Unfortunately, I've not installed Python on this. So, and Jupyter Notebook. So what it means is that you will be following what I've already done on the screen, the result. Yeah, but ideally I could be running it for you to be seeing it, but I could not. Okay, let's continue. We're looking at k-means, and we're saying that you evaluate k-means by using the number of k's. You have to decide on the number of k's. And in the deciding of the number of k's, you select the sum of squares within each cluster and you calculate. Once you do that calculation, you will eventually be able to get your elbow effect. Okay. So I want you to look at the figure on the bottom right. And in this figure, you will notice that there is a vertical line that shows where the elbow occurs. Now, the thing is that even if that vertical line comes, even if it doesn't show, you will see that looking at the lines as it descends, the blue line, as it comes down, there is not a clear-cut elbow from the first plot to the second plot. And there is not a clear-cut elbow from the second to the third. But from the third to the fourth, the thing actually properly bends. So that is why the elbow now actually appears. And in fact, there's a proper bend at the 7. So the elbow generally would have been between 6 and 8. But the clear elbow is at that 7. Okay. So the key point is that how do we do this elbow construction in our Python? Another method. So the elbow effect is a very powerful method, and it uses what is known as the sum of squares, okay, or the sum of squared errors. And we shall do that. The other example is, the computer is completely gone. Okay. So the other method is known as the silhouette score. The silhouette score. Now, what is that silhouette score? Well, what it does is that it calculates, the quality of the clusters, not just the number, but the quality of the clusters achieved by the clustering method. If you take a point like A in a cluster, so let's say in a whole cluster, you have a particular point like A, you can calculate the distance between that point A. Maybe when I draw, you get it, okay? Between that point A, and all the points in the clusters. So if there are other points in the clusters and you have point A, the distance between point A and every other one, that is going to, and that distance from that point A to any of the other points will be denoted by distance of XA. Once you have calculated that, the next one, you see, the software does these things easily for you, but it's always good to know what the software is doing. You will now average each distance, all the distances. So if one distance is 2, another is 4. Some of them are going to be positive, some are going to be negative. Okay, you average them between the point A and all the other points in the other clusters. And then you repeat the process 3 steps. You calculate the silhouette score for that particular point you've gotten by dividing the difference between the step 1 from the result of the step 2. So basically, the distance between A for Y and A for X, and then the maximum distance. The maximum distance is going to be bigger than between D, YA, and then XA. So the value is going to be 100%, basically. You calculate that silhouette score, and that is the silhouette score. You do that silhouette score for each of all the points, okay? And then after that, you will now average all of the scores to create what is known as the silhouette score. That's an example that you see here. And again, the software will calculate that for you. Okay. One thing is calculating the silhouette score. Another thing is interpreting the score. Okay. The score is always between -1 and then +1. When it is towards the negative, and then or 0, when it is around 0 and negative, it means that the distances are wider. Okay, so the clusters are very wide apart from each other. And then when you have a cluster of between 0 and 1, very towards 1, it means that the clusters are very well defined and the distances between the points are low. So in other words, they are very close. Now, if you are looking at between clusters, then you expect the value to be wider. But if you're looking at within clusters, you're expecting the value to be smaller. So that's why we say that the ideal cluster score is close to 1. 1 means that it's a perfect cluster. It will be properly, excellently, or perfectly classified. Okay. Now, here's a problem with the k-means, which will, like I said to you guys before, we are going to do the theory before we go into the practice. One of the problems of the k-means is that you compare according to the mean. Okay, so you are having a group and everybody is being compared relative to the mean. You calculate the centroid. The centroid is not specific to the data point. So when you have a particular data point like this, okay, I don't know why the yellow keeps coming. Let me just use red, which is more visible. If you have a data points like this and that and this, okay, and then you identify the centroid to be this blue section here. That blue section, you see, the way the mean itself is calculated, you can calculate a mean, and that mean is not one of the points. For example, if I tell you to calculate the mean between 2 and 4, and I want a better one, so that 2, 4, and which number will I add so that I get back 4? 2 plus 4 is 6. Which number would I add so that when I find the average, it will give me 4? 2 plus 6 plus what will be 4?
2.
6.
Yeah. Did you say 6?
Doc, yes, sir.
Yeah, 6. You see, simple calculation and some are sleeping. So that will give you 12. 12 divided by 3 will give you 4. So you see that 4 matches with the point here. So the 4 is actually one of the data points, so there's no problem. But the moment it's not 6, but it's rather 7, that gives you 13. If you divide the 13 by the 3, you no longer have a data point. And that is what the k-mean clustering is doing. You don't have a data point that matches with the mean. And so that is one challenge that we've identified with the k-means. Okay, because that means that you don't actually have the data point. You don't even have it if others are going to properly commit to it and copy from. It's not a role model. So the k-methods comes into the picture. It is a new version of the k-means, and that will give you an actual data point, not just an average of, it will give you an actual data point. And so it is more robust to noises and outliers. Now, if I were to ask you, which one is more robust to outliers? Is it the mean or the median? What would you say? Which one is more robust to outliers? It's very effective when there are outliers, Pascal.
The median, Doc.
The median. Why do you say so?
Because with outliers, it easily throws the mean of the actual representation. the real mean.
So with outliers, it throws what?
With the mean, outliers will easily throw the mean of the real representation of the group.
Yeah, so
It's median.
why would you say that it's good? If there are outliers, that's when it's good, isn't it? If there are outliers, that's when the median is good.
Yes, please.
But if there are no outliers,
Then the mean is preferred.
yes. So this k-medoid is related to what? Which one? Which of these averages? The mean or the median? It's related to the mean or the median. Adam,
The median.
the median. Have these things in mind. I'm just trying to espouse your knowledge. So what is the whole idea behind k-medoids? See, if you look at the word, the other one is mean. The second one is like median, medoids. Your goal is to ensure that the final center or centroid are themselves actual data points. That's the whole thing. Because when they are actual data points, you can interpret them and then you can also use them as a representative of the cluster. Now in k-medoids, we only change one step from k-means, which is a step around updating the centroid. Remember that iterative process where you have to go through it again and update. That is it. That's the step that you have to change. So instead of using the mean as the center of the cluster, you use the actual data point. Again, this is a sort of a repetition to what I said. Now, if there are m points in a cluster, you have to swap the previous centroid with all the other m minus 1 point, okay, until you get this k-medoid. And because of this, unlike the k-means, the k-medoid becomes more robust to outliers and it converges very fast. Okay, look, the graph is not too clear, but when you look down, let me see if I can zoom it. When you look down, you will see the difference between the k-means and then the k-medoid. Well, you might say that there is no clear-cut difference, but there is some sort of clear-cut difference. Okay, they're all dealing with a separate length. And as you can see, the center in the k-medoid, they are the actual data point. Check it. So if you look here, it is picking a data point. If you look here, it's picking a data point. If you look here, it's picking a data point. But when you look at the k-means, that star, that X thing, it may or may not be a data point. For example, if you look at this one, it's not too close, it's not on a data point. If you look at this one, it's away from a data point. And if you look at this one, there's no data point at the center there. So k-medoids is actually using the data points to do the work. Okay. What is a medoid? What are the algorithms, the steps, the procedural analysis for calculating the medoid? We've already said the medoid is a point in the cluster. Okay. And its distance with all the other points in the cluster is minimal. Its distance is the same as its dissimilarity. And the dissimilarity of the medoid and a particular point is calculated as the absolute value between the medoid and that of the point. If you want to go through the steps of calculating the medoid, first you have to initialize. You have to select a particular k random point out of the data and consider this as a medoid. Not medoid, but medoids, plural. Then you associate each data point to the closest medoid by computing using any common distance metrics between the methods. As you are doing that, you are reducing the cost. Okay. In other words, for each of the medoid m, for each data point, you are able to reduce the cost. And then you swap them because you now have P and C. You swap the medoid, associate each data point to the closest medoid, and then recompute the process. At the end of the day, the total cost, if it is more than the previous step, then you undo the swap that you did initially. Now, there is an example here for calculating the k-methods. Now, remember that I told you that we will go back to the calculation of the k-means practically. We'll go back to the calculation. But first, we want to know its alternative. So if you look at these data points here, you have a data point for each observation, you have an x and y value, and you can plot it using the usual Cartesian plane. You can see how they've all been graphed and plotted. The first thing you want to do now is to randomly select, and if you look at this particular example, the methods. Now, again, you have to press select. You have to select, you have to decide ahead of time how many methods, just like it means for the selection. So you take two groups. Okay, you select the K to be two groups. Now, don't look at the graph here to say that all the two groups are going to be this, or the two groups are going to be that. So let's select two methods, 2 points. Okay, now these 2 points are points we are selecting, which are 8 and 5, as you can see here for observation 4, and then 4 and 5, for observation 9. So we have pre-selected the two methods. We need to calculate their cost. We need to calculate the dissimilarity of each non-methoid point with this methoid that we've selected, and then we tabulate it. So how do you do that? First, you look at the distance matrices between the method and then the non-methoid points. So if you take the first point, okay, if you look at this very one, the point number 4, okay, the distance between it and itself is going to be nothing. And you can use a Manhattan distance for that. So you take the x1 value minus the x2 value plus the y1 value minus the y2 value. Let's start with this. Okay. What will be this value for the 4? X1 value minus the x2 value. And then the y1 value minus the y2 value. Now, if you look at the distance between C1, okay, so if you look at point number 1, 2, and then 5, okay, you go to the cluster 1, you will see that you have 0, 3, 6, and 7 that will also go to cluster 2. And then the cost, if you want to find the cost, you take the addition of the two, just as we have the x1, x2, and then the y1, y2, and you calculate the cost between the two. That gives you a cost of 11, okay, plus 2, 3, 7, 9, 11 plus 9, that will give you 20, okay, which you have here. And then you randomly select one of the non-methoid points and recalculate the cost again, okay? Now, we can let that non-methoid point be the 8 and 4. And then you calculate the dissimilarity of each of the non-methoid between this one. Each point will be given an assigned value to that of the cluster whose similarity is very less. So the point 1, 2, 5 will go to cluster C1, okay, and the 0, 3, 7, or 6, 7, and 8 will go to cluster C2. And then from that, you calculate the new cost as well. If you calculate the new cost, you're going to get 22 for that one. Then you swap. And when you swap, you calculate the difference between the new cost and the previous cost, which is 22 minus the previous one, which is 20, and that will give you 2, which is positive. Okay. Now you can see that the swap cost is not less than 0. Okay. So you will undo the swap, and therefore the 4 and 5, and then the 8 and 5 are the final methods. Now, when we come to the software calculation, you will see that this is fairly simple. Why do we need this at all? Well, from on top of your head, we've already said that it allows you to deal with outliers or extreme observations. It's very easy to understand and implement, and it's also fast, especially when you're using a software to deal with. But the disadvantage is that It's not suitable for clustering non-spherical groups. Okay, groups that have been arbitrarily shaped is not good for them. And the reason is because they will rely on minimizing the distances between the non-medoids, okay, and that of the medoids. And that is why if you are minimizing a distance and you look at something that is spherical, the distances are not circular. Okay, so if it is something like this, and you are even in the center here, the distance to this point is not going to be the same as the distance to that point. Okay, and it uses compactness as clustering criteria instead of the connectivity. And so ideally it's supposed to be dealing with a circular thing so that the distances match in that regard. Okay. Now we'll come and use this one when we come to the practical. So in the practical case of socioeconomic factors, we'll look at that. I've sent you that case study. We'll look at that when we get there. We can use the k-means with Python, which is what we are going to be using, or we can use the k-means with RapidMiner, the AI data from Google. Any of them, we can use it. When there's time, we will do both. Okay. The next kind of clustering is a hierarchical clustering. Apart from the partitioning, we spoke about a hierarchical clustering. Now, the partitioning, we've looked at k-means and the k-methods. Of course, the others. The hierarchical, we are looking at two as well. But first, understand what a hierarchy is. You are building a hierarchy of clusters, which means that some clusters are more important than other clusters. You are merging and splitting clusters based on their similarities. And that's hierarchical clustering. So you get something like a tree, and this tree is known as a dendrogram. The dendrogram, which is a tree, and you're going to see an example soon, and we'll run an example as well in Python. The dendrogram will tell you the relationship between the data points and the clusters. For each data point and each cluster, it will tell you. This is a very powerful method for clustering, and you can normally use it to identify relationship between data points and clusters. And some of you will use it. Not all of you. Majority of you will use supervised machine learning. This is an unsupervised machine learning approach. But some of you, a couple of you will use clustering approach in your work. So this is an example of hierarchical clustering. If you look at it, the one at the top, if we were to pick up the numbers, okay, if you look at these numbers, which numbers will you say it is at the top? Just on the left one in this dendrogram. Which number here on the left would you say is at the top? Is it 1? Is it 2? Is it 3? Is it 5? Is it 4? Is it 6? Yeah, Pascal.
To the left, it would be 5.
And to the
5 and 6, Doc.
okay. Who else? Angela.
Doc, please, I would say it's 6.
Okay. And the next? And the next? Rama.
Hello, Doc. I also think it's 6.
Yeah. And the next? Okay, you will have all selected. Yes. Who else is there? Angela Folaki Kuka. Is that your
Yes,
name? Is that a name, Angela?
yes, Doc, it's Falake.
Is that English?
No, please, it's Nigerian.
Okay. Okay, I'm pronouncing it like English. It's a Folake.
Yes, please.
And then the other one, the last one is what?
I would say 5.
Kuka.
Yes, Coca.
Okay. All right, so that's 6. And then you will have the next one to be a mixture of 1 and 3. Okay. And then the next one will be 4. Then from 4, you come to 2 and 5. Okay. We'll come and look at why this is so. Now look on the right-hand side. That is a typical example of hierarchical clustering. Now, based on this hierarchical clustering on the right, which one would you say is important? Which observation? I mean, this one you should know. In other words, which observation is not part of the whole thing? Which is more important? So you look at the bigger circle. Okay, what is outside a bigger circle? Then the next one, you come to the next circle. What is outside that next circle? Okay, and I know you know what I'm talking about. Then the next one, you come to the next circle. Okay, and the next circle is this one. What is outside that next circle? Then after that, you go to the next circle, and that circle, what is outside that next circle? And then you go to the final circle, and with that, what is outside that final circle? So you're able to compute you're able to find out the hierarchy. You are still grouping them, but you're grouping them according to the order of importance. Okay. Somebody has just typed something. I think I just saw it. Okay, so why is this important? Let's look at another one here. These are examples of hierarchical clustering. Okay, this is a traditional way of clustering. Okay, now in all of this, I'm using circles to do that, or spheres to do that. But the dendrogram will use steps like this. So if you look at this very one, okay, the traditional way of clustering here, okay, P1 comes first. P1 comes first. But when you come to the dendrogram will give P1 the highest hierarchy. Then after the P1, you go to P4. Okay. You go to P4, and the dendrogram will give P4 the next important belt. Each time you give the next important belt, you got to split it, whether there are others inside of it. And when you look at P4 circle, there are P2 and P3 under it. Now, just go back to P1. If you look at P1, there are, the only thing P1 circles is P4. When you put the circles around them, when you combine the traditional one, it makes it better. The only thing P1 circle and circles is P4, because P4 itself is encircling someone. Okay, but if P1 is encircling one group from the other, then P1 would have been split into that. But in the dendrogram, you can see that P1 has its own hierarchy at the top. Okay, and then you can have P4, which is the next circular movement before the others will come under P4. Now, in the case of P2 and P3, you cannot put one under the other. And the reason is because they've all been circled. The same thing comes from here, okay? But when you look here, you can see that this very circle, this is a non-traditional hierarchical clustering, okay? Because it's not going by that original. This is the same data point that you are trying to cluster. The non-traditional hierarchical clustering, and then its corresponding non-traditional dendrogram. You circle all of them together, so you give them one big circle, and therefore you are not able to say that P4 has the higher higher hierarchy. No, it's not on the higher hierarchy, but rather both of them, there is a higher hierarchy above both of them, and then each of these two groups will now split into creating their own non-traditional dendrogram. So watch the way the hierarchical clustering does, and then the non-traditional hierarchical, the traditional hierarchical clustering, and the non-traditional hierarchical clustering does. When we come to the practicals, you see it. Why is this important? Why wouldn't somebody want to use k-means and k-medoids, but a person would want to use this? Okay. Because here you don't assume any particular number of clusters. That's one good thing. See, unlike k-mean or k-medoid, you got to choose the clusters, assume the number of clusters ahead of time. Any desired number of clusters can be obtained by cutting the dendrogram at any time, at any portion that you want to cut it. And that will correspond to a lot of taxonomies, okay, step-by-step taxonomy. When you go into biological sciences in the animal kingdom, okay, in the animal kingdom, there's something we call, depending on where you were born, okay, that is when you give that particular term. It is known as a phylogeny, okay, where you reconstruct the evolutionary tree and find the best. Okay, that explains the sequence of data. When you want to backtrace the deoxyribonucleic acid, okay, or the DNA of a person, they use this a lot in biological sciences, and that is where the hierarchy comes. Now, some of you will remember the movie known as Root. If you were born a bit long time, if you are not a computer child, you remember the movie called Root, and they were able to trace, backtrace the genealogy all the way up to 7 to 9 generations, to find the root. So this is very useful when you want to, track taxonomies or track genealogies. But the one issue with the hierarchical clustering is that once a decision is made to combine two classes, you can't go back to it. You can't. So if you say that you're going to combine these two data points and then create a cluster with it, and then combine these two clusters into another, you can't undo it. And then there's also no global objective function that you're minimizing. If you can remember that of the k-means, there's a function you are trying to minimize the distances. But here, there's nothing really that you are using to do the minimization. We'll look at that when we come to the calculation, and you see that that's so basically you are using graphical approach to guide you. Also, there are different schemes, and these different schemes will have different problems, one or more. Some of them might be sensitive to noise. Sometimes you can have the difficulty of handling clusters of different sizes. Because the thing is that you are combining clusters, and some of them may have non-globally shapes. Sometimes you are breaking clusters. If the clusters are large, you cannot easily, because the larger it is, you have got to break it and break it and break it and keep coming down. And that is a tedious task. There are two types of hierarchical clustering. One is the agglomerative nesting. We call it Agnes. And the other one is Dinah. Agnes, and then where's the other one? Okay, you see that one later. So the agglomerative nesting, Agnes. Okay, what you do is that you start by considering each data point as a separate cluster. And then the procedure will iteratively merge the two clusters. So you've considered each one as a separate. So you have a data point, you consider it as separate, then you now try to merge those data points, the two closest ones, into forming a clusters until the data points belong to the same cluster. Then you now calculate the distance between the clusters using different methods, some of which are known as the single linkage, the complete linkage, or the average linkage. Now look at agglomerative clustering. So first, we merge very similar instances like this here, okay? We merge very similar instances. I know it might not look clearly like they are instances, but we merge. And then we gradually build a larger cluster out of the smaller clusters, okay? So you might have this 2 and this 3, and then you can now decide to combine each one of these. You are maintaining the set of sets, okay? First, what you do is that each distance in its own cluster is maintained, and then you repeat, and then add to it. Pick the two closest clusters, add to it, then merge them into a new cluster, and then you continue until there's only one cluster left in the end. So we say until it produces only one cluster left, but ideally you have a family of clustering, which inside it's being represented by the dendrogram. Yes, Angela.
Doc, can you kindly go over it again?
This one here.
Yes, please.
Okay. So first, you let's not even take this one that has been highlighted. So let's take this one here. Let me use this to combine these two. Okay. And then once I've combined these two, I now combine these two. I'm done there. Okay. And then once I've combined this, I combine that. I'm done there. Or once I combine this, I combine that. Oh. Hold on. Okay. Once I combine this, I combine that. And then once I combine this, so I'm adding to it, but actually I'm creating clusters and adding to the clusters, and eventually I will now have this combination. But then in total, it's like you have all of these combinations, but each portions was as a result of the combinations, okay, as a result of the individual combinations that you've done. So it is a step-by-step way of organizing the groups. It might be one, but you add one to it to form a cluster. You add another, but the steps in which you are adding to it, that those step-by-step approach in which you are adding to it, that is what makes it clustering. You are not just moving from A to B to C. No, not just like that. You are adding them by looking at the similarities that converged between them. And once again, when we come to the practical analysis, because it uses more of graph, when we come to the practical analysis, you better be able to understand, because we are not calculating. Okay, there's not calculation, but then there is an amalgamation of data points, graphical approach to data points. So let's take an example here that will probably give you a species understanding of what we are discussing. If you look at this, how should we define the closest for the clusters? Okay. They all have 3 elements. How do you define the closest? Suppose I want to define closest. Okay. Now I have between cluster here. Let me just name it. Okay. Let's call this A and call this B. And I want to, in fact, again, they are all similar, but ideally, let's assume that you have 1, 2, 3, and then here 4, 5, and then 6. Okay. If I want to combine, and I'm dealing with the closest here, okay, how should I define the closest for the clusters with multiple elements here? Okay, so let's first look at, I want the shortest distance, the closest pair. That is a single link clustering. Okay, which one will I combine? I've given you numbers so that you can just identify. Which one will I combine? Ajewa. Is it Ajewa?
Prof, I think the 2 and 3.
Okay, that's, you're talking about within, right?
Yes.
Yeah, but I'm talking about across the clusters. Those in cluster A with those in cluster B. That's what I'm combining. Okay, somebody else hand this up. Let me ask. Irama.
So I think 3 and 4.
It is 3 and 4. Do you all agree with that?
Yes, Doc.
Yes.
So that is 3 and 4. How about if I were to look for the farthest distance? That is what we call complete link clustering.
1 and 5.
On Tinubu. I want Tinubu to my friend. Okay. Judge Asante. Judge Asante, what would you say? Is it 1 and 6 or 1 and 5? I can't hear. Is it my network which is down or is his? Guys, help me. Is it his own?
Yeah,
It's not just network.
It's okay. I wanted to be sure that it's not.
Yeah, I said it's 1 and 5.
1 and 5. Do you all agree? Yeah.
Please.
Yeah.
Yes. And then you can have the average of all pairs as well. So different choices will create different clustering. Very good. So that is exactly what we just, let me just wipe this. That is exactly the answers that you just gave. So that is the agglomerative clustering approach. That is how you tackle it. Now, we are going to look at another one. Okay. Oh, this one is too obvious. Anyway, the answer is there. How should we define the closest for clusters with multiple elements here? So let's go to the closest pair. Okay. Single link clustering. If you look at the single link clustering, okay, if you look at 1, 2, 5, 6, 1, 2 are closer to each other, so we can start with that. 5, 6 are closer to each other, then we can now combine the two of them, okay, clustering. Then 3, 4 are closer to each other, so we can, fish them out. 7, 8 are closer to each other, we can fish them out. I wanted to just leave this one for you so that you can do it for me to see that. And then you can now do, now the closest pair, the single link clustering, if you can see it, I'm looking at the groups and then regrouping the groups. That's the whole thing. Okay. Now the farthest here, farthest pair, I'm looking at this vertical grouping instead of the horizontal grouping that you have here. So this is looking at the closest parent, and then that is looking at the farthest parent. Now, closest parent between 1, 2, and 3, 4. Okay. And then the farthest parent between 1, 2, and 3, 4, the same thing. 1, 2, and 3, 4 is farthest parent, and then 1, 2, and 3, 4 on the left-hand side is the closest parent. Now, let's convert this into the usual clustering behavior, the agglomerative clustering behavior. Check carefully. This is from a data set by Hasty et al. If you look at the nearest clustering behavior, you will see that even though you are dealing with hierarchical clustering, you can see that there's a lot of closeness. Okay. And then the average, there's not much closeness, but the farthest, there's a lot of distances. Okay. It's very wide apart. It's the same thing. All of them is the same data set, but you see a lot of closeness. So for the hierarchical clustering behavior, when there are lots of nearness to the numbers, you have a lot of dendrograms, being created in this fashion. Okay. Now, but the question is that, how do you converge? At what point do you end it? At what point do you end it? Will the agglomerative clustering converge? Will it converge to the global? Oh, in fact, I really wanted to ask this question. For some reason, my pauses didn't come, so you see the answers. But let's move on. Will it converge? Will we get to a global optimum? And the answer is it will converge, but it will never get to a global optimum. Why? Who can guess why? When you say it will never get to a global optimum, in other words, we will not get the best of clustering. Okay. Why? Because when you do each merging, you are doing it at the local level. You are doing the merging at the local level. But you cannot, you cannot break that down. We said it already. You cannot break that down and then go and then reevaluate later. Once you do it, once you converge, you're done. And that is why you can't. It's like trying to tell me that somebody in East Legon and another in Cantonment have got similar characteristics. So they move on. Okay. You make that decision, and now you want to now break that and then say that another, you can't do that with agglomerative clustering. Next question. Unfortunately, you see all my answers. Will it always find the true patterns in the data? And the answer is no. Why? Why wouldn't it find the true patterns in the data? Okay, because it's a heuristic algorithm. It's not you are not finding the best, the truth. It's not a truth discovery method. You can find a real structure under ideal condition, but you can mislead, when it comes to common scenarios. And so because of these disadvantages, sometimes people will think that you cannot use agglomerative clustering. You can use it. And some people are using it very widely. How many clusters do you normally pick? You don't know. You can go as much as you can in that sense. You can go as much as you can. And then we have seen that you keep going and keep going and keep going. That's why you can have many in the end. We said that there are two types of agglomerative clustering. The first is agglomerative analysis, agglomerative nesting. And the second is divisive analysis. What is the difference between the agglomerative analysis and that of the divisive analysis? I'll put both of them here in some few minutes. Well, the difference is that the divisive starts by considering the data point as a single cluster. Now, watch it. You remember the agglomerative, consider it, as individual and then start going backward to create the single. You guys remember? Okay. But this one starts by considering the data point as a big single cluster. Then it will step by step divide the clusters into smaller subclusters. Whereas this one starts by considering them as smaller subclusters, and then it will build them up. But this one will kind of start breaking them until each data point belongs to its own cluster. That's why it's called divisive. The other one is agglomerative. It's like adding. The division is based on the distance and the distance between the data points. Let's take Agnes and Dinah together, and let's look at an example. Now, even though I use the word Agnes and Dinah, it sounds nice, but please just remember the full names. Okay. So we have a data point of 5 objects: A, B, C, D, and E. In the first step, look at the way the agglomerative looks like. Okay, and look at the way the divisive looks like. So the divisive is like starting from the top, A, B, C, D, E. The agglomerative is starting from the bottom. So you can see that the bottom, you have A, B, C, D, E, separately on its own, agglomerative. And then what it does is that it combines A and B to make AB, combines D and E to create DE, and then picks out this DE and C and creates CDE, and then finally picks out AB and then CDE to create ABCDE. That is agglomerative. It starts from 0 step to the 4th step in that left to right fashion. The divisive starts from 0 to 4, but from the right to left. It creates that ABCD, split the ABCD into A, B, AB, and then CDE. Now, I'm just giving you a picturesque understanding. The question of, how did you get an A, B? And no, there's no specific calculation here. That is based on distances. I'm just showing you that is a picture way of trying to understand what is really happening there. And there's another way. Okay. So Dinah, you have all the points. That's the divisive analysis. You have all the points, then you split the points into A and B, and then from the A, you split into A1, A2, A3, A4. No. Okay. But then the Agnes is the other way. You have the individual points, 1, 2, 3, 4. You cluster point 1 and 2 into A. You cluster point 3 and 4 into B. And then finally cluster A and B into the final. So they're just more or less the opposite way of looking at it. So that is the Agnes and Dinah. So even if you didn't, these are all theories. That's why it sounds a little bit theory. When we come to the practical, believe me, you will get it. You will get it. Okay? Especially when you're seeing what is really happening. But even if you didn't understand anything about hierarchical clustering, There must be something you've gotten from hierarchical clustering before we go to density. Who can tell me what you have learned so far about hierarchical clustering? Before we go to density, and then finally we go to the Python. What have you learned? Okay, I'm just expecting anything that you've learned from hierarchical clustering. You are just supposed to be taking the notes and just tell me what you've learned. Class rep, let me start with you. You know I'm going to be giving marks.
Yes, sir.
Yeah, so class rep, get ready.
Should I answer?
Yes. Oh, no, if you don't want to answer, somebody can answer. I'm just saying that get ready to write down the marks for me.
Yes, I'm ready.
These are the ways you can make more. You can do well in exams. I was just marking research methods from last year, your colleagues. And then, in fact, some of them did quite rough, really rough. Really, a number of them. That word, some of them is an understatement. About 80% did very rough. So I said, no, let me push them. But then I must have a basis of pushing them up. What do you think will be the basis of pushing them up? I can't just give them marks. Because when I look at exam score and I look at the continuous assessment, the exams, they did nothing. So I need to now bring it to the continuous. I can't alter exam. I can alter continuous assessment. So I need to find a way around it. What do you think I did? Who can tell me? What do you think I did? If you don't know what I did, then you have already failed the course. You should have an idea what I did. Thomasia.
You use the marks that you allocate whenever someone participates to push them up.
Yeah. And I did that. And it really helped. Normally, that's a very last. I will still use it, but I use it, last because I know that one was end. And when I did that, the number of the almost 79% that were crashing. Okay, all of them did well except our 7%. So the 7% still were drowned. There was nothing I could do anymore, and they were drowned. And the reason is because they had 0, 0, 0, 0, 0, 0 in the class participation. So when I ask you anytime it's very important you are documenting things for me. Benjamin, is your hand up?
Yes.
Uh-huh. You want to answer the question?
Yes, please.
Oh, okay. Hey, now you won't even let me finish talking about the marks then. All right. So, Benjamin, start and let me see. And don't worry, I will determine whether what you said is palpable or not palpable. If you are copying too, I will know. Because I'll ask you a question. If I sense you are copying, so don't worry. Okay, Angela, let's start with you. Fitnat.
Prof, that the hierarchical clustering, it uses a tree-like structure, which is called a dendrogram.
Very good. Very good. So why is it called hierarchical? Still on you. Why is it called hierarchical?
Because it is split step by step based on their similarities or distance.
Yeah, but why hierarchical?
Because maybe because it uses two approaches, the bottom up and then the top down.
Yeah, but something must define that. Something must define you to using, bottom up or up down. You see the way your colleagues' hands are up. I was going to give you the 2 marks, but now I have to give you the 1 mark. Okay, let's go to rest for Nuno. Class, take note.
Hi, Doc. So to answer the question that you asked, I think that we call it hierarchical because it builds hierarchy amongst clusters. So then we can look at either the bottom-up approach or the otherwise. I think that's my response to the question.
Why hierarchical clustering? Yeah, why? You've said it all right, but you didn't really fully commit since it's a bonus. Yes, Brenda, question. Brenda.
No, I was making my own point. I don't have the answer for this one.
Then hold on. Let's deal with this one. I want to give the full marks to somebody who can make this one. So please, if you know you're not dealing with this one, then lower your hands first. Samuel Agbo.
Hello, Doc. I think it's called hierarchical clustering because unlike the K-means, which is sort of building a cluster like a cluster in, how will I put it? So this one builds a hierarchy from either bottom up or bottom down upwards. Unlike K-means where it's sort of localizes them in like either oval shapes or
Yes. So the idea of building the hierarchy is what? That's my question. As you move up or as you move down, the idea of building the hierarchy is what? That's all I need for this one. Then we move on. Adam, Kwame Beko.
Yes, sir. So the idea is to build relationships within the grouping data.
Is the idea
So
is to
it's to build relationship because
I
the
love
data.
that point. I love that point. But continue.
Yeah, because the data doesn't necessarily tell us how many clusters we are going to be able to do. So we use the hierarchy because when it builds the relationships, it is able to structure the ones that are close by and the ones that have meaning to themselves.
I'll buy that. Okay. So you are preserving relationships here. You are, and the idea is that you are building the relationship to be able to determine the smallest details to the bigger patterns. You want to detect the smallest details to the bigger patterns. That's why you're building a hierarchy. You're not building a hierarchy for hierarchy's sake. You're building that. Okay, very good. Now, so that's 2 marks for you. Who is that?
Yeah, so please, Adam.
Yes, Adam. Okay, that's 2 marks for you for that explanation. Now, who else can tell me what you've learned so far? I just want to take 3 more, and that's it. William Atamafo.
Yes, please. I hope you can hear me. So I realized that with the Agnes, that's the agglomerative, we see each data point as a separate cluster. Then as time goes on, we merge them to form bigger clusters. And with the Dyna, that's the divisive analysis. Each of them, all the data points are seen as one clusters, and it's further divided into smaller groups. And I also see it as a parents to children form of diagram
I love
where
that.
where there's
Keep
a
going.
parent with children below them. Thank you, sir.
Very good. I love that. I love that explanation. Excellent for 2. Let's go to the next person. Ebenezer Dete.
Yeah, hello, sir.
Yeah.
So today we spoke about hierarchical clustering. Now with hierarchical clustering, it's about nesting smaller or similar clusters and grouping them to find their differences, which constitutes their hierarchies. And then we spoke about agglomerative and then the divisive. So for the agglomerative, it's from the bottom down, which talks about all the points as individual attributes and then finding the closeness and grouping them. And then we also spoke of the divisive, which is top down. We start from all the data points at one and then clustering them into smaller groups.
That's good. Somebody has said all of this already. But that's good. You've been able to sort of repeat that whole process. And on the basis of that, I'll give you 1 mark for that. So that is good. There's something you've said that nobody has spoken about. Let's go to Kezia. Kezia,
Hello, sir. Hello.
go ahead.
Okay, so me, I'm also giving my own point.
I hope
I
it's
think
not
with,
about the same thing. Okay, don't
no,
worry. You go
no.
ahead. Go ahead.
I think with hierarchical clustering, it uses distance more, but this time it's visual. Like you have to see to group them visually. I don't know if I said it.
You say you don't know again. After you said
Okay,
it, you say you
sorry.
don't know.
Yes, but based on what I've learned so far, it uses distance more, but this time it's visual.
Okay.
What you see, then you group them. Yes.
Very good. Excellent point. I'll give you 1 mark for that. Let's go to Esther Dupo. Esther. Brenda question.
Yes, sir.
Hello, sir.
Esther, hold on. Brenda, continue.
Okay, you said K method uses actual data points as against K means, which uses the mean of the data. They
Very
don't
good.
use actual data points.
And what is so interesting about that then?
Interesting.
Yeah, what is so interesting? What is so good about that K method then?
You said something about outliers, but okay, let me see if I can sort of to say K means are somehow sensitive to outliers, but K methods are not.
Good. Now you're expanding. Now you're showing me you have arrived. That you have arrived. Brenda Bashi, 2 marks for that. Very good. Excellent. Okay, Esther, let me end with you.
Sir, please, I was about to also make that point about the K methods, where we use the median for clustering, and which is the actual data point, where the K means it doesn't point to the data point. So with the K methods, it gives a global the global
The global
optimal
something.
yeah, the global optimal. Yeah.
Very good. Very good. Yeah. Because she said it earlier, you didn't know what else to say, isn't it?
Exactly.
Okay. All right. Very good. So 2 marks for you as well. So guys, let's go to the last one before we go into the practice. The last one is known as the
I have a
density base.
question.
Yeah, go ahead.
I wanted to find out when you were talking about the agglomerative, you mentioned that it can converge, but you can't get a global optimum. So I want to find out, is it iterative? Because unlike the K image, you said you could keep doing the iteration until you reach the convergence point and get like a global optimum.
So on the basis of that, do you think it's iterative or not? You should be able to guess. It's not with just the K methods. Sorry. It's not just with agglomerative. It's with hierarchicals. It's all with the hierarchicals. So my question is, what do you think?
So when you say it's not just with
Because when we
the
say global optimum, okay, that is not what you are talking about as convergence. Because it converges. It converges. The only thing is that there is no global optimum, isn't it? And you're asking why it converges and there's no global optimum. Is that your question?
Yes.
Because when you take each merge is happening, at the local best choice. So the convergence is happening at the local. It's not for everybody. So it's like you're a champion in your corner. Okay, it is the locally best choice at that particular step, but you cannot undo it or reevaluate it later for the others. So you're a champion in your ghetto, but you're not a champion of everybody. And so because you're not a champion of everybody, you are not the convergence is not at the global optimum. It's not at the global convergence. That's basically what I mean by that.
Thank you.
All right, okay. Now let's go to the final one, and then we'll run the K-means. Yes, Saibu.
Doc, good morning. Not to take you back, I just have a question. So on the hierarchical, you say we have the Agnes and the Dinah. So I want to know, you see, the examples we've worked so far, we've seen like it's just a few points that you can point out and do your clustering. But let's say in the case you are dealing with a data set that is like in thousands or hundreds of thousands, right? You can just visually look at the points and decide which one to use. So how do you decide which of them to use? That's if you are using the hierarchical method. How do you decide which of them to use, whether you're using the Agnes or you're using the Dinah?
What do you decide? You have to decide ahead of time. Normally, when you are doing this, you do both of them. And then you use the evaluation method we spoke about to determine which one you like. Okay. It's just like any other supervised learning. Okay, you haven't done supervised learning. So you use both. Running both of them at the same data set is not difficult at all. So just note that you will do both of them. They are just two. You do both of them, and then you use an evaluation method to evaluate which one. And the evaluation method is going to tell you the lowest error that you have obtained from each one. And the one with the lowest error will be the method that you select.
Okay. All right. Thank you. Thank you, Doc. All right.
Density. There's something called kernel density approach. Kernel density. Okay. Now, the word dense has to do with how deep. Yes, James. Amuzu sound is up.
Hello, Doc. Sorry to take us back a little to the hierarchical clustering where we have the Agnes and Diana. When you look at the pictorial you've shown, one of them, Agnes, is clustering the letters, no, the one with the ABCD. Yes, so the first approach, we have AB up to E, and it's clustered step by step, and at the end, at step 4, we have ABCDE. The divisive analysis also look at it from the reverse side. So I want to know if the divisive analysis is a form of declustering, since it's more like breaking down the cluster into the various.
Yes, it's a form of declustering. Yes.
Okay.
Very good. All right, so the density clustering is a type of clustering that identifies clusters as areas of high density. So when the cluster is in an area of high density, separated by areas of low density. So you can say that a place is a highly dense, what do you call it? It's a densely populated area. Okay, a high density populated area is a place where you have a lot of slums and choked. Okay, most of the Okay, so let me ask you guys, would you want to live in a high densely populated area or a low densely populated area? Anybody? Godfred?
Low density populated area.
Good. Why?
Because with the high density, it will be like a slum. We'll be all packed together. Like you will know, your quality of life will be low because we are all packed together, and I don't know. It's just not ideal for human existence.
That is when you have defined that density as bad, isn't it?
Yes.
That is when the object I just spoke about is an object that is bad. But what if the one high density area is high income density area and then low income density area. Which one will you want to stay? Godfred, you now.
High density income area.
So it has to do with the object in question. Okay. Now, the idea is to group together data points that are close to each other and have a higher density than the surrounding data point. So in density-based clustering, your goal is to favor the high density. It is to favor the density, favor the closeness, and the closeness becomes better here. Unlike in a slum where the closeness is not better, here, the idea is that the closeness is supposed to be better. But what goes into it? Now, the interesting thing about the density-based clustering is that it is combining density-based approach plus hierarchical clustering. Or it's combining, it is together with, there are two methods basically for you doing that. One is the density-based scan, and then the optics. The optics combines the density-based as well as the hierarchical. But then the density-based scan doesn't combine that. The density-based scan is just using the density, or what you might call a kernel density approach, to be able to analyze the work. Now, how do you do it? You start by selecting a random data point, not going step by step, but you select a random data point. You identify all the data points that are within the specified epsilon or the specified region of that random data point. Then these data points are now considered the core points of a cluster. After that, the algorithm will identify all data points within this epsilon, within this error distance from the core point, and then it will add them all together. It will continue until the data points have been assigned to a particular cluster. Again, we'll look at how to work this thing in the real life. Why do we need too many clustering like that? Well, the thing about the density on its own is that you can identify clusters of varying shapes and sizes. You see, it is not just taking clustering together, but it's also looking at shapes and sizes, not just clustering because of similarity, but two things can be similar, but also the shape will matter. Okay. For example, I can give you $5, I can give you 5 cedis, I can give you €5, I can give you 5 pence. They're all 5, 5, 5, 5, 5. But there's a way you can cluster, because when you look at the €5, the size is different from the 5 Ghana. The size is even bigger than all of them, and yet the weight is not as big. So you are not just taking the value contained, but you're taking the shapes, the size, and so many other things related to it. And that is one thing the density base is good at. It can also handle noises and outliers. It doesn't need a number of clusters to be specified in advance, unlike the K-mean and medoids. And then it can be used in a wide range of applications as well. But it has a disadvantage. You need to specify 2 parameters, the epsilon and the minimum number of points needed to form a cluster. And then, even though it can handle noises and outliers, it can still be sensitive to the choice of that parameter and the distance used, the epsilon that you are using. Sometimes it may not work well with data that has varying densities or complex shapes. It can handle shapes, but if the shapes are complex, you see, there are some shapes that are square, 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 rectangle, rectangle, rectangle. But if there's some scales that are so many, trapezoidal and things like that, in that case, it is complex or curvy. But it's also, because it's dealing with a lot of complexities, you also need a lot of time. And so it can be expensive, especially in big data analytics. So that is the density-based clustering. Okay, so going back to the question I think one guy just asked, how would you know which one do you use and all of that? This is the way to handle that. Oh, wow. If I look at the time, it looks like we need to start We need to start the practicals now. Let me see. We are almost done though. Let me just rush through because I'll go through it in the practical. So when you're doing supervised machine learning, especially classification, examples of classification are logistic regression. Okay. You use things to dictate whether what you have done is correct. We use accuracy, precision, recall, F1, F, and all of that. If you are using regression, we use R square, we use F test, we use T test, we use adjusted R square, sometimes we even go to Okake information and then Bayesian information criterion and all of that. Those are supervised. Now, clustering is an unsupervised. So for cluster analysis, the analogous question is, how do you check the goodness of the resulting cluster? Clusters are in the eye of the beholder. So we know that. So practically, the clusters we find are defined by the algorithm. So why do we want to evaluate them if they are defined by the algorithm and the algorithms have been used multiple times and they are correct already? Okay, well, we want to avoid patterns in noise. We don't want to compare clustering algorithm. We want to see which algorithm is good. We want to compare two sets of clusters or even compare two clusters. So that is why we need to evaluate the clustering. So look at, for example, these clusters. Okay, they have been found in random data points. So the first one you see here is random points, just random, scattered. Now, they are scattered. We didn't have anything in there, nothing. Then we use k-means. K-means has given us how many clusters here? You can tell us. How many clusters has k-means given us? Angela?
3.
3. You used what? What did you use? Colors, right?
Yes, please.
Exactly. Majority of the time, a person will use only colors. But then do you realize that apart from the colors, there are also shapes there? Yes. Even if you don't answer, I know this there. Okay. So DB scan, okay, it considers the clusters, but also considers the shapes and the sizes of the shapes as well. Okay. That is exactly the point. So there are so many, approaches that you can use on this particular random data point. So how do you measure the validity, how valid the cluster is? Numerical measures, that you can use to judge the validity of the clusters. There are 2 of them: supervised approach and an unsupervised approach. Now, the supervised, they are used to calculate the extent to which the cluster labels will match externally, take note of that word, externally supplied class labels. One of them is the entropy, often called external indices because they use information external to the data. We'll deal with that. The other is unsupervised, used to compute the goodness of the clustering structure without respect to external, but you're rather dealing with internal. So that one will calculate the sum of squared errors. That's the one I told you about. Once you calculate the error, you want the lowest one. And it's also called internal indices because they use information from within the data. Now, the unsupervised measures, okay, we have, you can calculate the cohesion and the separation. The cohesion will tell you how close, the separation will tell you how wide apart. Okay, now the cohesion is calculated by the within sum of clusters using this formula here. So you're calculating cohesion using the sum of squared error, the within cluster sum of squares error. Then the separation is calculated by the between cluster sum of squares, not the within, but the between cluster sum. When you combine the two, high cohesion and high separation, then you have good clustering. So keep that in mind. Separation deals with between something. Cohesion deals with within. If you have done ANOVA before, if you haven't done, don't worry, look at it. But if you've done ANOVA before, you look at the differences between groups and differences within groups. Yes, among you guys are comparing MSBA with MBA student. Is it between or within? MSBA and MBA, is it between or within? Come. Go for it.
Between.
It's between. Okay. Now, within, okay. The MSBA, you have group cohort 1 to 6. Is it within or between? Pascal?
It's within.
Yeah, you get a point there. Okay, so you want high cohesion. High within, high between. That is good clustering. And you can use this method to calculate that down. I'm going to quickly go to this one. These ones are very easily self-explanatory here that you can use to calculate all of this. Now I want to go quick. And of course, apart from the SS, I've spoken about the silhouette. Okay, we'll use the silhouette as well. I've spoken about the silhouette we shall look at. I don't want to go too deep into this one. We'll look more at the then in the lab. So I want you to open your Python now. I want you to open your Python, your document I gave you. I gave you a latest document. Remember, my computer is gone, so I'm using this one, and I wonder if that particular, I wouldn't get it because I've not installed even Anaconda on this one. But I want you to open the tutorial 8. There's so many things are documented in that thing, but I can't open the laptop. Tutorial 8. Yes, Angela.
Doc, please, are you saying we should upload it to Python?
No, you should open it. You have already opened. Yeah. If it is in Python, you already opened Python, right?
Yeah.
Yeah, so bring that data out, tutorial 8.
Okay.
Everybody should open it. That's what I mean. I will need one of you to. There was an earlier. Okay, I need to go to my phone. There was an earlier this thing that I gave you. There was an earlier HTML file that I gave you. How do I get this? Okay. Yes, Valentina.
Drew, please, I wanted to find out if you would like us to share what you sent to us so that you can look through it while talking.
Actually, I want one of you to rather open and share your screen. That will help me because when you share it, this thing doesn't have the Anaconda yet installed. So I will not be able to. Do you get what I mean? I'll not be able to.
Yeah, that's what I'm asking, Doc.
Yeah, share the screen. Yes. So share your screen. You're a co-host, so you should even share your screen for us. I can't believe I can't even find the tutorial 8. But there was another thing that I gave you before the tutorial 8.
Hello, Doc. I think I've sent it to the chat.
Okay, good. Excellent. I think I have that here. Excellent. Oh, very good. So somebody is also sharing. The one I gave you, it is a kind of saved. But at least it's an HTML file, so you can pick it up from there whilst you follow through. So let me quickly walk you through. But this one is quite small. Anyway, it's okay. So you have a data set, and we are going to do k-means. It's a very simple work we are going to do now. It's a k-means. We know that k-means algorithm shows each cluster by the corresponding cluster centroid. The centroid here is a center or the mean. The k-means is a step-by-step procedural analysis. That is the algorithm. The algorithm will partition the input data into k unrelated clusters. And how does it do that? It does that by iteratively applying 2 steps. And you can see in point 8.1, the first step is to form a cluster by assigning each instance to the nearest centroid. Then recompute the centroid for each cluster. Now, this data set we are going to use contains the Python example for this very work. And go up, don't go down. Go up. Actually, this is not the very latest. Is this the very latest I sent to you today?
Yeah, you said the other one, we'll use it later.
Yes, please.
Okay.
This and the case
Go
study.
down, let me see. Go down, let me see what is the latest. Because there's something I'm expecting from the latest. No, this is not the latest. Yeah, this is not the latest. I sent you something today, which is this one. Who has it?
Okay, Doc. So we should share what we have today.
God,
Because you
have
said
you
we
had
should
breakfast?
Doc, please, is it the one on the case study
ask
for the
me.
clustering?
Yeah,
Not a case study.
one.
Tutorial 8. Let me see if I
Okay,
can comment on.
Doc, I'll check and then share down.
Not a practice case study.
Okay.
Yeah, just before the start. Oh, it's not you people. No, it's you. Just before the statistics for business analytics video I sent you. Some of you are now commenting on it. I said, use this. That's the one. Yeah, if you can please share that for us. Now, whilst she's opening it, okay, remember that this is in the book, and I've given you the book, which is Introduction to Data Mining. Okay, but the key point of clustering is to partition the input data into groups. Okay, related instances, so that instances that belong to the same clusters are grouped together. And then those that are not are parted together. So what we are going to do in this tutorial is to provide an example of using clustering technique provided by the scikit-learn library package. You guys have used Jupyter Notebook before, haven't you? You are doing programming for analytics, right?
Yeah.
Good. That's it. So you've used it. So this is not a time where I'll tell you, load this one. No. You know it all already. And you can see that you can use both the coding system whilst you also treat it as a Word document. So you can treat it as a Word document whilst you use this one. Okay. So we are going to do the 2 approaches. And we are waiting for Tina to load. Very good. Go up now. Go up. Yeah. That's it. So go up now. Go up now to let the data set come and then make it slightly big if it's possible. Good. Click inside the import pandas as PD and all of that. Okay, I'm sure you guys know about pandas. Okay, very high, package for dealing with tables and multiple analysis in Python. Jupyter Notebook is just an extension of Python. You can also use Python. Okay, I love that one even more because it can do more iterative works. Unlike Jupyter Notebook. Jupyter Notebook is not able to effectively export things to HTMLs and other things. So this is a data set, which as you can see, it is a ratings of movies, 4 different kinds of movies by these individual people, 6 people that you know, John, Mary, Bob, Lisa, Harry, and all of that. Each of them is rating a particular movie known as Jaws, Star Wars, Exorcist, and Omen. Now, even if some of you have watched these movies and some of you know these movies as to whether they are action-packed or they are horror. Now, what the owner, or let's say Netflix, want to know is he wants to classify which one of these people is actually going for these movies. Okay. Now, first of all, we need to classify the movies into how many groups. But on top of your head, you know that these movies are already classified into 2 groups. What are they? Into 2 groups. What are the 2 groups? I mean, just on top of your head. Esther.
The horror and then the action movies.
Okay. Now, because the data is small, you can easily say that, oh, I think this guy like horror, I think this guy like, and all of that. So let's pick an example. Watch movie. I'm going to ask you, is this person a horror fan or an action sci-fi fan? Let's take John. Who can tell me? Just looking at the output. And by the way, in order for you to be sure that this thing is running, let me see the names first before I ask the question. Caroline.
Hello, Doc. John is an action fan.
What makes you say it?
Because from his, you'd see that with the movie Jaws and Star Wars, he has higher values there compared to the
Higher
Exorcist
what?
and Omen.
Higher what?
Like 5 higher values.
Yeah, what shows that higher is better? It's because you're not getting the proper word. That's why I'm asking you the question.
Okay.
Let me go to another person. Brenda.
Doc, these are ratings, so he's rated the action movies higher than the horror.
That's it. So you've told me that they are ratings. So you've rated something as higher. Okay. Now I understand that it's ratings. Okay. I want you to run the command because right now they are all 1. So whoever is sharing, please run the command. You should have some errors, maybe. Okay. So in your case, what is William saying there? Sorry, what did you say?
I did run the command and then it
Yeah, it's
worked.
fine. It's fine. It's shown the data set is fine. Sometimes you will get a command run, but then depending on the nature of your computer, you may have some memory lot there. So it will not allow. But in your case, it has. So no problem with that. Next. So when you look at it from the data, okay, watch the way the things were written before the results were shown. Because if I give you an assignment, you are going to run them yourself. So you need to know how you are actually creating your data frame for that. But in any case, these are movies that you've shown and you have the writings. I've given you another command that shows another way of doing it. And I did this for a reason. That's why I had to change the thing today. So in this command, you can see that I've imported not only pandas, but also NumPy, matplotlib, as well as the scikit-learn that we know of, from which you can get the k-means. So I've imported all the necessary libraries that you need for this. In the first command, we are creating the data set. And you can see that here I've made it A. I'm scrolling your screen as if it's mine. So go up rather. So if you, no. Go to the, yes. If you look at the previous command, you can see that they were horizontally arranged, the ratings. But here, you can see that the ratings have been vertically arranged. So it kind of makes it easier to look at it. That's number 1. Go down. Number 2, you can see that there are a bit of commands that included. Okay. You have the titles as usual, but you can see that there's a command on how to prepare the numeric data. And you can see that we are also dropping the user column. And the first one, we called it movies, but here we are calling it data. Okay, just to separate the two. And you will see later on why I did that. So again, this shows the data set. Let's go. Our goal is to apply the k-means clustering approach on the users. Identify the groups of users with similar movie preferences. But just on top of your head, you've all confirmed that action movies, the Jaws and Star Wars, and the horror movies, and The Exorcist and Omen. Now, this command, you can see that I want you to remove the import iOS, just delete it. And the next one, the OS environment, the first two rows, highlight and cut before you run. And let me see something. Again, it was my computer that made me change the environment and run it. And let's see the results. Good. I think you've also had the same thing there. So you can see that with this command, you get a certain warning, isn't it? In fact, all of you should be running on. You get a certain warning. And that warning is a very annoying warning. It doesn't stop you from getting the answer, but it's a very annoying warning because it's creating a chunk, of information than what is available. And normally to correct it, you have to set the environment variable to the thread. That is why I made you cut. Now you can go and paste it and let's see. And rerun it. Now, do you always have to click? You can always do Ctrl Enter. You rerun. In your case, you didn't even solve it. Or you haven't rerun.
I did rerun.
All right. I'm sorry. It looks like your computer has more problem than mine. Let's move on. Anyway, so in order to avoid this, decided to now not take this command. So we go to the next command. So this is the original command. So we go to the proper commanding. We are going to train the k-means with two clusters. Now remember, stop here. Remember that we are deciding ahead of time that we are going to use two clusters. And that is something we have in mind. But we'll later check whether the two clusters are sensible. And so we're going to train the k-means by writing k underscore means equal to the k-means formula. The n clusters tells you the number of clusters. The maximum number of iteration is 100, but we use 50, so it's okay. The random state is always set to 1. And we are going to fit the model. Okay. Then the next command, after you fit the model, you will find which clusters will give you action movies. Now here I've renamed it as action sci-fi versus horror. We are going to calculate the average rating for Jaws and Star Wars for every cluster, for every action. Now, because, and you're going to see this problem if you use the earlier command. The earlier command, if you don't tell it that I want you to use these names, action and horror, it will rather use the group as 0 and 1, if it is two groups. If the groups are 3, it will rather use the groups as 0, 1, and 2. And I found that to be quite annoying. So what I decided to do is that I have to code it so that it will stop, renaming. It will stop using 0 and 1. Because you see, the thing is that when you later tell K means that, okay, I want you now to tell me which person is watching action movie. He will use 0 or 1, but that 0 might be horror or action. It's just random. But then I don't want it to be random because on top of the data set, go up to the data set. Go up to the data set. Go up to the data set. Go up. Scroll up. Valentina, is she there?
Please, I'm here. I'm
I said scroll
scrolling
up.
up.
Look, you are showing everything, so you have to really pay attention for us. Your screen is not moving, eh? Guys,
Yeah,
can you
please,
hear me?
can you see my screen?
Your screen is
Valentina, your
not
screen is not
Can
scrolling.
you see my
moving.
screen?
We
Oh,
can see it, but it's
sorry.
not moving.
Okay.
If you are not this thing, can you let somebody take over?
No, please, I mean it. I don't know why it's not full. It's not showing it.
Looks like your machine is frozen.
Wow. I mean,
Yeah, others
I'm
have
so
done it.
high.
So you can stop sharing. Who can share for us
Okay.
and sort it out? Time is running. Angela, do that for us. Are you sharing, Angela?
Yeah, Doc, I've sent a request.
Really?
Did you see my screen now?
It's coming. It's yet to come. It's yet to show. All right. So you go down. So this data set, scroll up now. Yeah, this data set, just by looking at it, you know that person one, you see the way Python has called it, person one, he called it what, 0, isn't it? Meanwhile, the name we gave to it was, go up. The name we gave to it was John. John. And yet he's not using the John. He's now, because we've removed the username. The same thing when we combine JAWS and Star Wars as action, it will code it with a number because it's coding it as a binary because you use 2 clusters. And I didn't want that. So I need to recode that. Look, anytime you're going to call something 0 or 1, use the following so that it makes sense. So let's go down and see that code. I just hope that you guys will understand what I did. And I know you've run all of this, so no problem. So now here, stop here. So in here, you will notice that I have indicated that action cluster should be renamed, as 0. And horror cluster should be renamed as 1 minus action cluster. Do you see that? Do you guys see? In number 4.
Yes, please.
Okay. Now, once you've coded that, you can now create the cluster names and allow the cluster names to be used, allow the labels to be used. So you can see that the cluster names have appended the naming to be action sci-fi fans. Okay, and I've indicated using a Boolean that it should be renamed as horror fans if it is actually a horror. So everything that is for horror or 0 will be renamed as horror fans. And then the other one for action sci-fi fans will also be renamed. Then in command number 6, we are going to combine the names with the descriptive clusters we have. So wherever you have the user, we are actually using the name that we used. And then for the cluster names, we use the name cluster. And then finally, we can print the results using the proper cluster assignment we have. Okay, so do that. Run this, because you haven't run it, have you? Or you've run it already? So that you yourself can fill it. Yeah, it shouldn't work because you've not done the previous one, the k-means. When Valentina was running, you weren't running yours, eh? Were you
Doc, I
running
did.
yours when she was running hers?
Yes.
You are muted. Run the command here. Run this command. No. Run this one. Yeah, this one. And then go and run the next one. Yeah, number 3. No. No, you shouldn't have run this. But let's move on. Number 3. Now, when I say number 3, I mean, you see in the code, I've labeled them with blue. Blue as 1, 2. Run. Then you go to 3 and the rest. Run. Okay. Now you see the results has come, right? Is she with us?
Yes, Doc.
Not only you, it's for all of them. So I hope they are all following. Okay. So guys, go up, let me show you. So you can see that this one, it gives you the names. It gives you the names. It tells you that the user person is John. And John has been assigned as someone who watches action movie. And therefore he's an action fan. And that the last person, Harry, is what? Is a horror fan. Now, the previous code wasn't doing that. This one, so each one has been properly classified according to action or horror, not according to 01, as the previous code I gave you was giving us. Okay. So the K-means clustering algorithm assigns the first three to action sci-fi cluster, and then the other three to the horror cluster. And when you can see, the results are in agreement with our mind, because we know that, John actually rated Jaws and the other movie high. So our expectations are fulfilled. Okay. But we want to get a centroid for each of the clusters. And then I'll tell you the mismatch that happened, which is now you're not going to use, I changed it. And the reason why I changed it is because when you use original code, there's a mismatch. I've told you already. There's a mismatch between the 0 and the 1. You see, K-means uses the 0 and the 1 arbitrarily. It doesn't care whether it is horror you want the 0 to be or 1 you want the other one to be. Okay. They don't carry that intrinsic meaning. They just assign numbers to clusters in the order that they created internally themselves. But I didn't want that. So here, what I've done is that I create a mapping the old label to the new label. So the old label is what? 0. So we call 0 will be action, and then horror will be 1. And then we apply that to our clusters. And then we'll run the mean. So show the centroid now by running that command. I know the results are showing here, but you have to run it to confirm. You got it? Where's the result? That's it. So you can see that it has created a cluster ID. Okay, because you indicated that in the fifth row. It's created a cluster ID so that you know that the 0 is actually referring to what? Action. And then the 1 is actually referring to horror fans. This we know already. Now let's run the centroid to be sure, because it must agree with the centroid. No, the one above it. So you are just trying to identify the center of the ratings. That's it, the center of the ratings. And you can see that the 0, the Jaws has gotten what? All the 3 groups. Okay, the mean, the centroid is 4.3 for Jaws and 4.7 for Star Wars, which means that this group, and you are calling it 0, right? But now we know what 0 means, because at the top, we know what the 0 means. The 0 stands for action, which means that truly Jaws and Star Wars are action movies, and they were actually selected by those who are action sci-fi fans. Unlike Exorcist, they also rated Exorcist all right, but then the centroid they gave to Exorcist and Omen were very, very small. So you can see that cluster 0 has got a higher rating for action movies, whereas cluster 1 has got a higher rating for horror movies. Believe you me, if you had not done the recoding, they would have swapped. That's why it's very painful that Python will do that, because you have not coded it properly. So this cluster centroid can be applied to others. Okay, so what this means is that now that we already know that, anybody who is in this cluster 0 is an action fan, and anybody who is in this cluster 1 is a horror fan. The moment you add somebody into the group, we can predict. This is where predictive analytics come in. We can automatically predict that, oh, this person is going to be what? An action fan. Oh, this person is going to be what? A movie fan. We don't need to even do it. We just need to use the centroid that we've created automatically to find them. And we are going to do that in this next column. We are going to use the trained k-mean model above to predict which cluster the new guys will belong to. So I have to redo the whole thing again. So these are the new guys. Okay. The new guys have got names. You can see under the username, their names are Paul, Kim, Elizabeth, Tom, and Bill. And Paul's ratings are 4, 5 for Jaws and Star Wars, and 1, 2 for Exorcist and Omen. That's the one at the top, test data. You see, we are calling it test data because that's what we are going to use for the prediction. This is not part of the trained data. The training data is the one we've done already, and this is the test data. Okay, so we are now going to predict the next information instruction. You're going to predict which cluster each new user belongs to. And we are going to give the test data proper columns. Okay, so we create a data frame called test DF. And in that test DF, we have created Jaws, Star Wars, Exorcist, and Omen as the columns. And then the labels we had originally, we have it there, and we're going to use the k-means to do the prediction. And then, once again, we have redefined with a Boolean function, okay, that we should map the numeric cluster labels to a descriptive name. So we want the descriptive names to show. And we use that Boolean that for the labels in that if and else, we use all of that. You've done this in programming for analytics. And then with that, you can build the new users using the test data. And of course, indicating that if a new user belongs to action, label it as 0. If the new user belongs to this, label it as that. And so we don't even want to use the 0. We want to use the clear names that a practical person will understand. And then you print the result. I'm just going through these tests for you to know that these are not just code, but they are meaningful codes. And that will give you the final result here. Run this result and be sure that your code is running fine. Run it. Hopefully to show the same thing. Good. It's showing. So what do you see here? New guys came into the picture. You see, we didn't run them. We just used the existing, centroid. And this new guy, Paul, you can see that straight away he's an action fan. Okay. You can see the next guy, Kim, straight away you can see that he's a horror fan. Guys, the key point is that this data is small, so you might think that, but we know, we can look at it and we know. But life is not like that. Netflix is dealing with thousands and thousands of movies, millions of megabytes of data every single day. And so there's a lot going on. But by having this data, you don't need to worry yourself. You can see clearly what each person actually likes. And now that you know that this guy is an action fan, Paul is an action fan, when you are using recommendation system, this is another machine learning model. When you are using your recommendation system, you will only recommend action movies for Paul because you know that Paul is going to stick and stay with Netflix. And so that's why you see a lot of, Netflix will tell you that since you have watched this movie, these are movies you should watch. Or since you watch this, these are, I'm sure you guys can remember some of these things. Okay, so now we have been able to use this for prediction. We wanted to predict whether Paul is an action fan or Kim is not an action. We've seen it all. How do you now tell the number of clusters in the data? The original one, I mean. The original data we had, the number of clusters, we chose 2. How do we know that the 2 is sensible? We got to use the elbow effect of the sum of squared error. We will match the sum of squared error, we're going to calculate that very soon, against the clusters, the number of clusters, to be able to estimate whether the 2 that we selected was good or 3 is better, or we should have done just left it. Now, the command you see here, the 23 command, that one didn't show me the nice one, so I had to recreate the command. So you can go to the next set of commands, starting with the 2. Go down. So in this command, you are going to compute the sum of squared error, and we are calculating that for k, which is from 1 to 6, for all of them. Okay, we don't know which. So we'll create an SSE, that we don't know yet, and I give a k range to be between 1 and 7 inclusive. We have just added a 7 to just go a step further. And then for each k, we create a k means. You see that here we have indicated that the number of clusters is k because we don't know. It can be any of them. The maximum number of iteration is 100. The random seed is set to 42. Okay, and these are all standard. And then we can fit this data by look at the next important one. We can now append the k-means or the inertia approach, and then calculate the sum of squared error, which is the actual inertia. And then we can plot the results. The result we are going to plot is the elbow curve. And the elbow curve is going to tell us which number will be the cutoff point for the number of clusters that you should select. I've renamed all of these things, so you can choose your own name. This is the first one. The first one is nice, but it's not the best because it doesn't really show. If you have a lot of data points, that first one might not give you, because it's so plain white. But the second one is great. Okay, the elbow method for the optimal k, because that one has got a kind of a graph in there, and the graph can easily tell you the number of clusters you are supposed to select. So, ladies and gentlemen, just looking at your results, how many number of clusters are you supposed to have? It can either be 2, 3, or 4. Which one? I left that there for you. And you got to give me a good reason why it is not the other. Okay, 2, 3, or 4. Samuel.
So I think it's 2, because that's where it's actually the curve is sharp coming from left to right.
You think it's 2, because that's where what? Yeah, that's where it's not clear.
That's where it curves. That elbow can be seen.
But somebody might say that, stay there. Why are you going down, Abaya? Somebody might say that, but it's also curving at 3, because the 3 is also on the same level as 2, or what? I'm just worrying.
In my opinion, it's sharper at 2 than 3.
Okay. I'm just worrying you. I just wanted to be more confused, but that's it. It's 2, okay? Because that's the first place the elbow happens. Everything else, 3 and 4, are all on that same level as the elbow. But the first elbow happens at the 2. And therefore, the number of clusters to select is 2. When you're doing your longest, you use the same thing. You should use the same approach also. Okay. So, guys, this is how you are able to now do k-means in your work. Any question on this? Any question? Now, the question might be, so if you are using your own, how do you go around these things? Sometimes somebody say, how do I know the code I need to write to be able to do this? Has any of you asked that question before? Anyway, you haven't asked me, so I will assume that you know. But if you want to ask me, you can ask me and then I will answer. Valentina.
Okay, Prof. I was actually thinking of asking you.
Sawala. Sawala.
Because
what's your
if
question?
we have, so please, if we are going to write this on our own, how do we go about it?
If you are going to what?
If we are going to write the codes ourselves, how do we go about it? Because sometimes we know that you can write certain codes and you run, it gives you errors and all that. So if we are going to do this by ourselves, how do we go about it?
So first thing you want to do normally is you want to copy, or you want to slowly work with this example I've given you. That's the first thing. Okay. There is a chat GPT, not exactly chat GPT, but it's different. What's the name? It's called OpenAI, I think. Is it OpenAI? It's something. And you can use that to guide you. Sorry, what's the name?
Copilot.
Oh, Copilot is also good. But this one is purely designed for coding, whereas the Copilot is for everything around. You know, this one is designed purely for coding. You can also try Grok.
Claude AI.
Sorry?
Is it Claude AI?
Claude AI, that's it. That's it. Okay. Claude AI. So use Claude AI because it's purely designed for, you know, more of coding things than the others. Yes, Imananati.
Hello, good morning, Doc. Please, my question is also related, but it's slightly skewed. In exams, are we supposed to remember all this?
No. In exams, you are going to be given some graphs, some instructions, then you can, the reportage I gave you, you're going to be given a reportage like that. Then you are asked questions related to the report. So for example, using the graph below, discuss what would be the appropriate number of clusters to be used. Which groups have been properly classified, and they have been classified into what? In other words, you should be able to read the results. The other one sort of question you will get is, suppose you have been given the data, like the one we did last time. You have been given that data, use k-means, okay, with k equals to maybe 1, k equals to 2, and use that to be able to properly classify them. You know that one, we did that classification with the C1, C2, and all of that last time. Do you remember? So that one is manual calculation. And this one is when you have been given a graph or some tables and you are being asked some questions related to it after you have been given the preamble. Master, does that answer your question?
Yes, Doc.
Good. Don't worry. I have some questions for you, which will be assignment. There's more of assignment as well that you'll be doing. Anyway, so what's going to happen is that next week, next time we are going to look at hierarchical clustering application. Okay, you can see it is down here. But we are not going to do it now. We're going to continue and look at hierarchical clustering. Then we'll look at all the divisive, the Agnes, and the Dyna, and then we'll look at even dbScan and Gaussian mixture and all of that. We'll look at all of this. But you can go through it. You can go through it slowly. You can see that what you are looking at is not looking neat. Okay, you are getting a flare of the hierarchical clustering right here. Scroll down. And then there is another one, which I've also given you, which is the socioeconomic planning. The density-based clustering is also here. We'll apply all of them. So go through them before we meet next time. Any question? There are more that we didn't do, but they are here. Like spectral clustering. But that one is just simple one. Okay. So if there is no question, who teaches you statistics for business analytics? I know you have two separate groups.
Dr. Hanan Jacob.
Okay, good. And then the other group.
Dr. Bo.
Okay, good. Well, you still have videos, which I've sent some of you to watch. Okay, you still have some videos